Team, welcome back. So we have good amount of attendees now. So let's start up the session. Okay, the session is the debugging the issues on the bootloader. Basically, this is a known issue many customers face. For any embedded project, usually customers tend to keep bootloader application, bootloader code, and the main application separately. So sometimes customers may end up in the issue. Am I audible now? Hello? Okay. Thank you, Divya. So I was telling debugging the bootloader issue. The reason for taking up this topic was not all the customers may face this issue, but this may be the issue when customers want to build a project or build a product where there is a bootloader separate and main application separate, and their customers may face the difficulties because bootloader is also a code again, software code, or take it as a firmware code, and the main application is also a firmware code. But we have to tell processor clearly at reset which part of the code the processor should execute. So basically it is bootloader. So processor has to execute bootloader, and there should be some way to transfer the control from bootloader to application. So usually this transferring of the control has to be taken care in your project development, or the programmer developer who is developing the code. So today my focus on this webinar will be how to start up with a bootloader, then how to get your code processor to shift to the main application, what are the criteria you have to take care, what are the main things you have to consider. Okay, so there is no real demonstration or something, but this will give you a fair idea if at all any of you are facing this issue, or you have some projects you are expecting to be done in the future, or some current ongoing projects. Okay, so let's start the session. Thank you, Satya. Let me share my screen. Please excuse me, guys. I have very bad throat. My voice may go down, or I may cough in between. Please bear with me. So hope the team is able to see the screen. Are you able to see the screen? Okay. Great. So the main topic of this is debugging the bootloaders and the startup. Why I'm using the word startup? Because mainly the startup is the main important part of the code in your project, which many people ignore or quite ignorant, because the startup code will be in assembly usually, but there is an option of developing the startup code in C as well. So the main things, modifications, everything you have to take care in the startup code only. Okay, so that's the reason I have taken the topic. I have given the heading as debugging bootloaders and startup code. So basically startup code is what we have to modify, and this is where the startup code will guide the processor how to it has to start execution, how the processor flow should be. So this is with the Keil IDE I'm showing, but this concept remains same for irrespective of any IDE you use. So the agenda will be ARM Cortex-M boot process overview, bootloader architecture and implementation. Those these words feel a bit heavy, but there is nothing like thinking that, oh, this so much to understand. It's very easy. I'll just explain you in this session. And we'll go through the startup code analysis, which many engineers, many users tend to ignore. Many things can be done with the startup code. We can modify the startup code. What all is part of startup code? I have already done a detailed webinar, that is world before hitting the main function. I had done a webinar on that. So there I had given a detailed explanation on what is startup code, why anyone should be more concerned or more pay attention on startup code. Then we will see some debugging techniques with Keil MDK. So now coming to ARM Cortex-M boot process. So before starting, please put your questions on the chat. Okay. So I do have some time allocated for Q&A session. So I'll come to that at the end of this session. So first is ARM Cortex-M boot process. So how the processor boots, because Cortex-M is a simple architecture compared to ARM7, ARM9, though ARM7, ARM9 is a legacy ARM architecture where still customers tend to use it because of its availability and ease of programming. But there, a processor operates in 6 to 7 different modes, operating modes. Whereas Cortex-M is very simple. It's only 2 modes. There is privileged mode or unprivileged mode. Okay, so we have to know how the processor starts. When you give the reset, suppose you have loaded the code to the board, when you give power on reset to the hardware, how the Cortex-M processor boots. Okay, that is all where you have to, this particular slide is how the processor boots. The processor boots by reading 2 different memory locations of your um, memory present on the device. Okay, so usually it will be flash memory, or because it's an ARM, even through JTAG debugger, you can load the code to the RAM. Okay, if you're loading code to the RAM, you have to do some changes. I'll come to that later when I talk about running the main application. So now we are now talking about the boot process. So usually it will be the flash address. So it will read the address 0 and 04. So basically 0 is your reset handler. Basically, reset handler is also highest priority exception in Cortex-M. So when you give reset to the processor, that exception has to be serviced by the processor. That should be the first exception, because it's the highest priority exception compared to all other exceptions in the Cortex-M processor code or in your application as well. So it starts from 0th address. So reset handler means we should now guide the processor. Where is that handler routine? So there is an exception handler routine which is written in the startup code. So I'll just quickly open the Keil. Thought of opening it, I didn't open it. Okay. So that just if I say like that, you may not understand. So this is your startup code. Okay. As I told, the processor first reads 2 different entries. So these entries are editable, means as I said, the processor will read the address 0 and 4. 0th address is where the processor will understand what is the initial stack which is available for the processor to start its execution. Excuse me, irrespective of whether it is bootloader or main application. Why I'm telling irrespective is because not all projects require bootloader in the main application. Some may be just pure main application without any bootloader concept. So first is what is the stack available for the processor. Second is the reset handler. This is basically the program counter, because now in this reset handler routine, there is a definition. There is a exception handler routine which is written in this startup code. So through this memory, through 2 memory locations, processor will start booting. Cortex-M processor will start booting. So reset handler. So coming to reset handler, this is your reset handler. So this is written in assembly. You can modify this easily. Okay, anything you want for the processor to do in the reset handler, you can do it. You can add the code, assembly code, to this block actually. Okay, so we'll come to this a reset handler in depth when we talk about startup code analysis. Okay, so this particular just now is to show you. It first fetches the initial stack pointer and the reset vector. Reset vector is nothing but your reset handler, which is nothing but the program counter. You know what the functionality of program counter, right? So that is the register which the processor reads to know from where the processor has to fetch the next instruction. So execution begins from reset handler. As I said, reset is the highest priority exception. Then system initialization and transition to the main. So as of now, we will just remember system initialization, and from there, from the startup code, the main processor jumps to the main function, whatever the user has written in their C program. But in this system initialization, what all happens is what I'll throw light when I talk about analyzing startup code. Because at the agenda, we have startup code analysis as well. Now, default C library initialization. So here in the startup code, if you see, so you can see here, first is system initialization. Then it does the main __ main. Many of the users get confused this __ main with the actual main program what the user has written. This __ main is nothing but the entry to the C library, ARM C library. So that is what this shows. Image point entry is __ main. It's not actual main. Okay. Then from there, it does, if it is any copying, what is this copy? Sometimes what happens, we load the code to the flash, but we want the code to be executed from the RAM. So code has to be copied from flash to the RAM. So all those can be done by this library function, __ main. Okay. This is not editable. This is not transparent to us. We cannot edit that. Okay. So where do we do this? In the scatter loader file. Then __ main will call the RT entry. What is RT? Real time. So real time environment, it initializes. What does it do? It initializes the stack and heap. You know what is heap, right? In a RTOS application or wherever you want dynamic memory allocation, you're using any malloc, calloc and all, then we have to initialize the heap memory there, and then only processor will be able to allocate the memory from that heap. Then initialize some library functions, then some constructors. From there, from RT entry, it goes to main function. And from main function, you always write return. When you give return, it exits from the application and it comes back to the C library. This is how it's a closed loop. Okay. Now coming to reset and initialization. Cortex-M processor startup and privileged thread mode. Okay. The startup code, whatever the startup code you're writing, the processor always executes that in a thread mode. What is thread mode? It's a unprivileged mode of execution of the processor, but only for the startup code as an exception. It executes in the thread mode, will be executed in the privileged mode. Privileged mode means it has access to all the CPU resources, memory resources, memory peripherals, all the CPU related parameters it can access. Then system initialization can only be executed in privileged mode. So what does the system initialization do? It initializes the clock and memory for various peripherals of that particular ARM MCU what you have selected. So this can be they can be if the controller what you have selected has a MPU, memory protection unit, or enabling the interrupts to NVIC. All this is because Cortex-M is based on the memory map registers. Means for each configuration of each peripheral, core peripheral, or even if it is a device peripherals. When I'm talking about when I tell core peripherals, it's the peripherals inside the CPU. It can be NVIC, it can be MPU, it can be SysTick, it can be watchdog timer, or it can be, wake up interrupt controller. It can be anything. So though there are core peripherals, there are the registers mapped to these peripherals for the initialization. Okay, so MPU and NVIC, vector interrupt controller, nested vector interrupt controller, these are all part of system control block, SCB, which for the processor to access that block, it should be in privileged mode of execution. The processor should execute in privileged mode of execution. Okay, but the developers have the choice of running the main application in privileged mode or unprivileged mode. So this is main important. Before entering the main application, the startup code might need to perform the following things. You have to set up the MBU, enable the MPU, if at all MPU is provided by the silicon vendor. Then stack has to be 8-byte aligned to avoid the wastage of stack. Unaligned stack is still supported, but it end up in using the extra bytes of the memory, because stack is very crucial. So have to be very careful for any embedded application. Complete any memory remapping. So that's what I said. Processor, we can execute the code from flash, we can execute from on-chip RAM, we can execute from off-chip RAM, off-chip flash. So you have to clearly tell to the processor from where it has to execute. That is where your reset handler goes. Okay. Suppose if you are executing the code from the flash, you need not modify vector table offset register, VTOR, which I'll talk about in the coming slides. If it is you're loading and executing the code from the RAM, then VTOR has to be set as per the starting address of the RAM. If it is off-chip flash, if it is off-chip RAM also, it has to be set accordingly. Why this VTOR is required? Vector table offset register means your startup code has not only the entry for the processor, but it also has the exception handlers for all the core exceptions. So you can see here, reset handler, NMI is also, there is a non-maskable interrupt, that's also an exception. You have hard fault handler. Any issues which happen in your code execution, the processor will come and stop at the hard fault. Okay. So hard fault is like a master exception. Any issues, any problem happens in the code execution due to related to some memory not available or address not available or whatever it is, the processor will come and stop at the hard fault handler. Then we have dedicated memory manage handler. We have dedicated bus fault, usage fault. So memory management is exceptions that arise due to MMU, if at all memory management unit is defined. Bus fault is if there was any issues happened while fetching the code or fetching the data from the buses, internal on buses. Usage fault is this exception can be generated based on how the users write the code. Okay, so I'm transitioning between MDK and slide for you to make understand what are those exceptions, and this VTOR, based on what address you give, these exceptions will be offsetted for that specific address, so that processor will not have any issue when any such exceptions or interrupts happen. Okay, once before processor leaves the startup code, before it switches to main, it changes the mode of the processor execution from thread mode to unprivileged if required. Means your main can execute in privileged mode or unprivileged mode. Now we saw the first preliminary initialization sequence. Actual initialization sequence when it comes with the CMC startup code. So CMCs, I believe many of you know, because Cortex-M is very popular in the market now also because of this IoT application related stuff, and Cortex-M is widely used in this edge devices for AI application or ML, whatever it is, even for sensor application, even it for Bluetooth, or it is for some wearables or designing. Everywhere Cortex-M is used because of its scalability and the availability of the wide range of processes. So CMC stands for Cortex Microcontroller Software Interface Standard. So this startup code is given by the silicon vendor. What do you mean by silicon vendor? So if you have selected an ARM microcontroller device from NXP, or ST or Nuvoton or Nordic or Microchip. They have to give this startup code. Okay, so this startup code is, it will have your reset handler. It will have the entry for all the core exceptions as well as the interrupts generated from the various peripherals of the device. Because this includes all the device peripherals, and peripherals change from one silicon vendor to another silicon vendor. This specific has to be, this startup code has to be given by silicon vendor strictly. Okay, so now from reset handler, it goes to __ main, which is your C library. From there, this normal starts. Only one entry was added now in this possible initialization sequence. We will again hit this same slide with the modified versions. Okay, so here, I can quickly go through. So these are all the vector table for the various peripherals of the specific device. Suppose here it's selected 1768. So 1768 has all the peripherals. Like UART, I2C, SPI. You can see here itself. Watchdog timer, we have 4 timers, we have 4 UARTs, 2 I2C, SPI, this is extra interrupt handlers, ADC, USB, CAN, all this. So for all the peripherals, there is a dedicated interrupt handler. When you come to reset handler, first do the system initialization. This initializes all the system or correlated peripherals. Usually it initializes the memory and clock for the various peripherals of the device. Then it goes to the __ main, which is the entry to the C library function. Okay. And then it, after returning from __ main, it branches to the actual main function. Okay, so this is the same thing what I explained. So I'll just quickly move this slide. Now the same slide, possible initialization sequence. Now we added previous slide with CM reset handler. Now we are adding user setup stack heap. Now from reset handler it goes to main. From main it goes to RT entry. From here this he initializes the library runtime environment, basically the stack and heap. If you want, you can also give your own definition for stack and heap. So either the processor can use 2-region memory model or single region memory model. 2-region means you can use heap and stack, or you can use only stack depending on what is your application or project requirement. So you can define this user setup stack heap. So I can only define this particular function and specify from where my stack starts or where my heap starts. All those information I can define that in this user stack heap. So where does this function come? It's here. Everything is there in the startup code. See, this is user initial stack heap. This is the same function what we saw in the PowerPoint slide. So this we can define as per our requirement. Okay. Next possible initialization sequences. After this RT entry, after users setup stack heap, from there it can go to, before going to main, we can have one more subset of the main function, which will do the initialization of the NVIC, MPU, wake up interrupt controller, or watchdog timer, or any such correlated peripherals like SysTick, all this. From there it can call the main function. Okay. So for bootloader implementation, it's always advisable that bootloader starts with a different address and the main application starts at a different address, so that we can give the program counter correctly. Now you may ask me the question, so does both the projects have different startup code or one startup code? The answer is yes, both the projects will have different startup code. In the bootloader application, we will execute from startup code, run the bootloader, and from bootloader is again application for because bootloader is again a software code. There again we have to give a jump to the main application. So in the main application, there is a startup code where the reset handler will directly it will directly go to the address of the main application. So that way you have to keep two separate projects, one for bootloader, one for main application. So jump to application has to be ensured from the bootloader. The startup code analysis, we already saw this. Now coming to debugging techniques with the Keil MDK. So suppose you want to debug the bootloader, as I said, because you have two different projects. So you on the same hardware, you can connect your JTAG debugger, whatever the device you're using. Even we offer ARM Ulink debuggers, which works seamlessly with Keil. It also supports JLink from Sega. So there are many third-party debuggers which are supported by Keil. So you can select any one of those debugger, connect to your hardware, and start putting a breakpoint or seeing where the processor is stopping its execution, when the processor is executing the bootloader correctly, or bootloader is mapped to this correct to the address what you have given. Is it at the correct address? All those you can see it from the debugger. Basically, if you want to see bootloader is a map at specific address, you can check that from the map file as well. Okay, there is a map file which the linker generates. I would request the team to keep the map file always handy, because all the memory related information, where the linker has located your code, where is the main code, where is the data, where is the symbols, any functions are removed from the final output file generated by the linker. All the information related to the memory, how the memory is being used, how the memory is mapped, based on your code and data, how linker has mapped it. You can have can check it up from the map file. So always keep the map file handy. If you want, I can quickly show one. Excuse me. So here it will tell in the map file what compiler I use for building the project, that you can see here as well. 6.22 latest version, but latest is 6.24. So this is your local symbols, symbols whatever. This is all from the C library. So this is all your SysTick global symbols. This is all your C __ main. This is your C library entry. This is your actual main. You can see blinky.o or text.main. And this is all the address of where my handlers are located. So support reset handler is at address E1. So like that, any address related information, exception handlers, like execution address, load address, what is the size of the section. Wherever you see the star, it's a library entry. And always your processor starts execution with reset, which is at the 0th address. The 0th address is where it will find the stack pointer and all. So all the information, I'm just showing you. Any memory related information, you can find it from the map file. Okay. So in the debugger, you can put a breakpoint. Suppose anyway, when you run the program is not running, bootloader is not running or something, or your main application, you can keep two different instances of Keil ID open, and you can debug single step, put a breakpoint, like a normal debugging. You can use it and you can test your program. set VTOR. VTOR is your vector table offset register. So this has to be set to the reset handler of the application. As I said, both main application and your bootloader has a startup code, correct? So the first startup code will tell the processor to execute the bootloader code. Then from the bootloader, it has to jump to the main application. Main application startup code is also there. But there, we vector table offset register is set to execute. Tell the processor has to execute from the reset handler of the main application. Okay, so how you set that? Through the VTOR register. If you refer any data sheet of the device, you will get to know the VTOR register fields. I believe many bits are reserved in it. Only lower 16 bits or something we can specify the address. Okay. This is best practice and tips is, if at all you don't have hardware also, you can still use the simulation mode or simulation models which MDK offers. We call it as fixed virtual platforms. There are actually platforms which are developed by ARM for some specific already designed boards or modules developed by ARM. So that if it is based on Cortex-M3, you can still use that. I'm just giving an example. You can use that for any of your project based on M3 like that. But simulation models will help you to at least find out how the code executes on the processor. If not, it may be because the simulation models, peripherals, and your application peripherals may not match, but still you can see how the processor core performs, like Cortex-M core, irrespective M3, M4, M7, whatever it is. Okay. To get more details on MDK, so we probably can refer to MDK documentation. There is a lot of technical reference manual available on arm.com. There are two sites basically I would recommend. Go to arm.com for all the information on ARM processes or technical reference manuals or user's guide on how the programming can be done, everything on the arm.com. Developer.arm.com is specifically for whatever the software solutions offered by ARM, specifically like Keil, or it can be JTAG debuggers, evaluation boards, FEPs, simulation models. So all those information. You can get it from developerarm.com. Okay. So basically, the session was to tell you how you can control the processor to execute from bootloader, and from there how it has to jump to the main function. Sorry, I don't have any ready demo example to show, so I could not arrange any real live demonstration for that to show the scenario. But I know some customers who are working on such scenarios, so I thought let me address those issues. So any questions? Let me come there. Okay, so I don't see any questions here. So I'll give you time for you to, if you had any questions, or you want me to suggest any topic for webinar for the next month, because probably I didn't introduce only. I'm Geeta. I work as Director ARM Tools at GSAS MSPL. We are the prime and authorized distributors for ARM software solutions in India. So more than 2 decades of experience on ARM technology and ARM software solutions. You can please reach out to me on my mail ID, geeta@gsasmspl, or even on my phone number. Probably I'll put it on the chat. And I would like to get any feedback on any specific topic the team wants to expect me to do a webinar, so I'll be able to include that in I can take that as a topic for my next month webinar. So these webinars, what we conduct from GSAS, it's purely technical webinars showing how ARM surface solutions will ease the life of the development team on like whatever it can be debugging related, or with the help of the technology or the software technology, software compilers, how you can expedite the development of your product and bring the product to the market on time. So that is the view, and that is the focus for all our technical webinars. There is no commercial stuff. Satyam, expected question. Okay. Yeah, I'll try to. FEP, I've already done a webinar, Satyam. Basically, I have done the webinar on simulation models of ARM, and probably I can take an extension of the same webinar on FPP, and probably I can arrange pre-silicon platforms. Can you please pre-silicon in the sense Ganesh, your question is not clear. Pre-silicon platforms, Cebu Palladium platforms. Well, Ganesh, if these are based on ARM, yes, I would love to take it. But let me first see what are these platforms. I haven't come across these names, sir. Sorry for it. But I'll make a note of it for sure. Pre-silicon platforms. Okay. So this is my mail ID and this is my phone number. Okay. So Satyam, I'll come with one more probably extension of that FEP webinar, and I'll try to arrange for a demo. Can you tell memory-related errors, which handler taken? Okay. Misani, your name. Narasimha Misani from Australia. Okay. So coming to memory-related errors, there are two ways. If there is any error happen in your application, the processor can go to hard fault handler. If the memory error is related to the MPU, if the device what you have selected is an MPU, because it's an implementation specific, means the silicon vendor will decide whether it has the MPU, whether the device has an MPU or not. Okay, so if the device doesn't have MPU, it can still go to memory management handler, provided you have defined it in the startup code. Means you have given some address for that in a startup code. If you have not defined that in the vector table of startup code, the processor will come and stop at the hard fault handler. As I said, hard fault handler is a master handler. So as soon as when you stop the processor execution with the debugger, you'll see just that processor is stopping at the hard fault handler. So because as the word suggests, hard fault handler, there is nothing to get panic. There are fault address registers which you can find out from the fault status registers. You can find out what was the actual fault which caused the processor to come to hard fault handler. Was it the bus fault? It will show you whether it's a bus fault, memory management fault, or usage fault. Again, if it is bus fault, you can go to BFSR, that is bus fault status register, whether the issue was from the code program bus or the data bus. Memory MFSR is memory fault status register, to tell whether the error happened when the processor tried to fetch the code from the flash or the RAM, or when it failed to update the contents of the RAM, or whatever it is. So you search fault like that, you have status registers, and there are associated status registers again for that, to understand why this exception happened. Any other question? Okay, if you have no questions, please note down my email ID, geeta@gsasmspl. Feel free to send me an email. You're welcome, Nasima. Okay, you all these email IDs will get a link for the webinar, recorded webinar. Okay, so please feel free to suggest me a topic, or if you have any query, any specific to the ARM execution, like Narsima asked, or anything on any suggestion on what device you have to go, or software, or any related to embedded project requirement, you can please send an email to me. So I'll be able to answer your questions. Even if it is basic, you can ask the question for me, no problem. Okay, thank you, team. Thanks for your time. Thanks for making up for the webinar. I'll see you soon in the next webinar. See you soon. Bye-bye. Have a nice evening.